Hello, welcome to my Topic 6 integration presentation. In this presentation and specific slideshow, I will be going over the basic introduction of integration, including definite and indefinite integrals as well as antiderivatives and its relationship with differentiation, as well as other key vocabulary and concepts. After this introduction, I will be going over various examples of different functions and how to integrate all of them utilizing different rules and formulas, some of which include the chain rule, addition rule, and product rule, and as well as other rules. What is integral calculus? It essentially involves anti-differentiation and is the reverse process of differentiation. It contains many different applications, some of which include finding area under the curve, finding volumes of revolution, distances from velocity functions, and other problems such as that in economics and biology, and many other applications also. Differentiation versus anti-differentiation. Well, we know that differentiation is finding the derivative of a function, while anti-differentiation is the reverse of this, since it can be used to find the original function of the derivative. The product of this process is called the antiderivative. As you can see in the cycle over here, you use differentiation to find the derivative of f of x or f prime of x, and then you use anti-differentiation or integration to find the original function. So over here you can see a cycle where one can be used to find the other. Indefinite integrals. Over here you see an example of an integral and its solution. As you can see, over here marks the integral sign. Over here marks the integrand, which can be a variety of different functions. Over the course of this presentation, I will be solving many different types of integrands and finding the integral of each one. Every integral, well, at least an indefinite integral, has a constant of integration. As a rule, it is known that the derivative of the constant is always equal to 0, which is why it is never seen in the integrand. However, it is very difficult to solve for without any other context or information. So you typically, when solving for the antiderivative of an equation, you typically add a plus c to represent the constant that is unknown to the equation. D of x also represents the variable of integration, while the solution, or capital F of x, is the indefinite integral, or most also known as the antiderivative. Over here we see indefinite versus definite integrals. From the previous example, we saw an indefinite integral. Over on the left here, you see an A and a B. These are known as the intervals of integration, where B represents the upper bound limit and A represents the lower limits. Typically, Antiderivatives are applied to indefinite integrals and aren't typically related to definite integrals. Over here we have the fundamental theorem of calculus. It essentially shows the link between differential calculus and the definite integral, or rather limit of an area sum. As you can see in the graph, we have the equation y is equal to f of x. What the fundamental theorem of calculus essentially states is that the area between B and A is also equal to this equation as well, right over here. So using this integral, this definite integral, you can be used to find the shaded region in the function in between the 2 points, or rather the area under the curve. Up next, we have the rules for differentiation. Before we learn more about antiderivatives and antidifferentiation, we need to just quickly understand the rules for differentiation. Some of you might be wondering, why exactly must we know differentiation when we're trying to find the antiderivative? Well, the reason for that is being that it's a complete cycle. As seen in one of the earlier slides, we know that one can be used to find the other. So, in other words, you can use differentiation to find the derivative and then anti-differentiate the derivative to find the original function. So, it's basically a back and forth cycle where one can be used to find the other. So it's very important to understand the rules for differentiation since they can provide a basis and better understanding as to how the function came about and help you better grasp the overall process. So some of the rules for differentiation are as seen over here. So first up, we have the power rule, we have the addition rule, we have the product rule. Next, we have the quotient rule. Then we have the chain rule. And utilizing these rules for anti-differentiation. For example, like in the power rule, as we can see, finding the derivative of the function would be subtracting 1 and then multiplying by the exponent. However, for antiderivatives, you would essentially do the reverse of this. So instead of subtracting 1 from the exponent, you would add 1 and divide it. So that's basically the opposite of what you are doing here to find the original function. The same applies for addition rule, where you would just apply the power rule, well, the specialized reverse power rule for each term as its own individual. So over here, we have some rules of anti-differentiation. As you can see on the screen, we have a total of 3 rules. There's one other rule that we will later be going over. But the first rule essentially states that the antiderivative of e of x is basically e of x. And similar to the e of x rule, the antiderivative of sine of x is negative cosine x, while the antiderivative of cosine x is sine of x. Oh, pardon. Is sine of x. Over here we have some complete equations. So solving for the antiderivative of e of x dx would be equal to ex plus the constant. The same applies to the other two equations, as these are complete equations. So there's no guarantee that there's no constant in the original function. The last rule for integration is as shown as follows. This rule basically says that the antiderivative of 1 over x is ln of x, as x is greater than 0. So in this equation as shown, we know that the antiderivative of 1 over x is equal to ln of x. Next up, we will be going over indefinite integrals. The next rule we have here is the power rule. When applying it to differentiation, you would subtract x1 to the you would subtract 1 from the exponent and then multiply it by f of x. However, for anti-differentiation or integration, you would add plus 1 to the exponent instead as the first step and divide by the exponent from which you added 1 to. So in this scenario, you would add 1 to 2, so then it would be x equals 3. And then for the second step, you would divide 3. So then the answer for this integral would be x to the third power over 3. If you were to find the derivative of the solution to this problem, you would get the original function as shown here, x squared. This is an example where you would use the power rule to solve the problem. As you can see, I'm adding 2 over 2 or 1 to the exponent. So by applying the power rule, the antiderivative of this is x to the 3 over second power, and you would also divide by the exponent. Or you can also do this by multiplying reciprocal. Over here, I'm also simplifying the equation. And adding the constant. And that's our solution. This is another very similar question to the previous one. Over here, you would use the addition rule, where you would treat each term individually and apply the product rule on all of them. So as you can see here, I'm rewriting the equation and replacing the 1 into 1 times x to the power of 0. And as you can see here, I'm also doing the power rule for the first term, where you add 1 to the exponent and then divide it. Over on the second term, while you can't really see it, the x is still present, and you would add 1 to it. So you're basically adding x into the number, and then you get the solution. This is another slightly more difficult problem. You are essentially doing the same thing as with the addition rule, except for the fact that there's a constant that can be factored out. As you can see, the 4x and the 2x have a coefficient which has a common denominator of 2. So what you would do here is factor out the 2 and then solve it as so. From this point onwards, you are also using the rule as previously mentioned in the slideshow, where the antiderivative of cosine is also sine. So doing so, you would get this solution plus c. Plus c. Yeah. Okay, so next up is differential equations. In this problem, we have to differentiate dy over dx, which is equal to negative 1 over x cubed. So the first step to doing so is to isolate dy by itself. After doing so, you would integrate this and solve for y. Through this process, you would get an integral for which you would use the power rule, and then the solution of which would be equivalent to y plus c. Further simplifying this, you can convert the negative 2 exponent into the denominator. Okay, so next we are going to solve for the constant of a differential equation. So given that you know what the derivative of f is and the value of f at 1, which is equal to 2, the first step to finding c to use to find f of x is by solving for the antiderivative as you would do normally. So what I've done here was that I converted the derivative of f of x into exponent form, to which I will use the product rule to solve for the antiderivative. Okay, so from this point onwards, the first step would be to solve for c. So we know that 2 is equal to the derivative of f at 1. So we know what the equation for f prime is. So what you would essentially do is plug in 1 into that equation and then solve for c. From which you would get c is equal to 5 1/2. then to get f of x, you would use the antiderivative you solved earlier, except plug in the c that you just solved for, to which you would get f of x, and that is your solution. Another way we can solve integrals is through the reverse chain rule, which is essentially the opposite of the chain rule. Over on the top left, inside the chain rule box, you can see the formula for the chain rule as used in differential calculus. So if you were to basically take the derivative of f with respect to g of x, that would be the equivalent to the derivative of f with respect to g of x times the derivative of g of x. So essentially, with the reverse chain rule, you're treating the inside function and its derivative as the outside function. With the chain rule, the reverse is also true. For example, as you can see in the expression at the very bottom, the derivative, the antiderivative of f of g of x times the derivative of g of x dx is equivalent to f of g of x plus c. It is important to note that you are essentially taking the derivative of the inside function and multiplying it by the outside function to get the antiderivative. Over here, we have an equation where you would use the chain rule to solve. So as you can see, I'm substituting the inside term as u, and by doing so, you would get the integral u to the 12th power times d of x. Except, however, while you are substituting one, you must also substitute the other. So by solving for the derivative of u, you can find d of x and substitute that into d of x, to which you would get du over 6. And then since it's 1 over 6 is a constant, you can factor that outside and then use the power rule, or rather chain rule, from here on. And then solve for the antiderivative. At this point, the final step is to just plug in u, and then you would have your solution. So over here, that's u, and then I'm going to plug it in and simplify it. And that is your solution. This is another more difficult problem where you use the chain rule. So instead of one inside term, this equation has two inside terms, to which you would find du and then solve for dx for each of them. Over here, I'm going to integrate them each separately. So you get e to the power of u times -1, which can also be factored out. And then the antiderivative of that would be negative e to the power of u. And for the second term, you would take out the 4 since it's a constant, and then plug in du over 2 as dx. Simplifying that further, du over 2 has 1/2 as constant. So the 4 would turn into a 2, and then that would be your new integral. Solving it, it's 1 over u2, so the antiderivative of that would be ln of u2. Now that we have solved for each term, it's time to put them together and subtract them to find the solution. And then plug in u and u2 and add c, to which you get your final answer. Next up, we have definite integrals. Over here, we will be learning about limits as well as how to apply limits of integration with chain rule. Before we learn more about definite integrals, we first need to know what is a limit. Well, a limit is the value that f of x gets closer to as x approaches a certain number. As you can see on the left, that certain number is infinity. So we are solving for the number f of x gets closer to as x approaches, or rather n in this question, approaches infinity. And as we can see on the right, the limit of f of x as x approaches 3. That is what this equation is signifying when we are solving for limits. You might be wondering, what's the point of using a limit? Why don't you just plug in the number and just solve for 2 like in this equation? Well, the reason for that is being that there's some scenarios where that's not a valid solution. Since in the equation as shown here, if you were to just plug in 1 into the denominator of x squared minus 1 over x minus 1, well, 1 minus 1 is 0. And you can't divide by 0 because then the whole equation would be undefined. Well, we see that the solution is 2, but looking at just the function over here, we know that it can't be 2, since if we were to graph it as seen on the right, there's a hole, or where it's not equal to. So the limit is basically solving for this hole, since it's impossible for the equation to be equal to 2, as it would be undefined, thus there being a hole. So we cannot say what the value of x equals 1 is, but we can say that as we approach 1, the limit is 2. So before we start learning how to solve definite integrals, we first need to know its properties. As you can see here, we have a list of 5 different properties of definite integrals. The first property, sum and difference, basically means that you can split from this region over here to this region over here, and then split this region over here, g of x, into its own separate integral. That is as long as the upper bound and lower bound remains the same for both of them. Our next property is the constant multiple property. So this basically means that for every constant, you are able to factor it out. So as you can see here, k represents the constant of this equation, and that is equivalent to as if it were outside the integral. This is because regardless of its position, it wouldn't really have an effect on the total output, since it's not a part of the function, so it's able to be factored out. Our next property is the reverse integral property. So by switching the upper and lower bounds, you would get the same number, except it would be a negative or a positive if this integral were, if the solution to this integral were negative. So basically it's the opposite, since the direction to which you are calculating the area under the curve would just be reversed. Our next property is the zero length interval property. This basically means that if the intervals are the same, as you can see here, a is the upper bound and a is the lower bound. Since the intervals are the same, that would mean the solution to this equation would be equal to 0. That is because the difference between the same number is basically 0. So that would eliminate any other number and result in the solution to this equation to also be 0. Our next property is the adding intervals property. This means that by adding it, as you can see, a to b and then b to c. So that would be equivalent to a to c. Since the upper bound is b and the lower bound is a, that is the area under the curve from a to b. But then the second expression over here calculates the area under c and b. So by combining this, you are basically calculating from a to c. So this is the other property. As you can see in this slide, you can see an example of a definite integral. And a definite integral is different from an indefinite integral in that it has a limit of integration. As you can see in this example, the limit of integration in this case is a and b. Where as a is on top, it's the upper bound limit, while b on the bottom is the lower bound limit. So the way you solve this is to use the power rule in order to get this section right over here. In this question, the upper limit is 4 while the lower limit is -1. So the way you solve it after finding the antiderivative is by using the upper limit and just simply plugging it in to the equation and subtracting it by the product of when you plug in the lower limit. As you can see here, 4 is plugged into x cubed over here, and it is subtracted by -1, or rather the b, to show the lower limit. Solving these two, you get the solution 65/3. Okay, so this is another example where you would use limits of integration to solve this definite integral. Over here, I'm using the chain rule to substitute 2x and d of x, to which you get dx is equal to du over 2, and then substitute it as so. Since du is over 2, 1/2 is the constant and it can be factored out. And the antiderivative of sine is negative cosine. So you would solve it as so, where the antiderivative is literally negative cosine of u, or 2 of x. And over here, I'm putting the upper bound and lower bound. So from this point onward, you would plug in the upper bound into cosine of 2x. I also factored out the negative to make it a little bit easier. So then you would plug in pi over 2 and then subtract it with cosine of 2 times 0 over 0. Since cosine of pi is -1, when you subtract it from 1 or cosine 0, you will get 1 as your solution.